Welcome to Altair Engineering Training and Support. Today in this video I am going to discuss how to perform torsional analysis for roll cage structure, which is done by doing 1D elements meshing. So we'll first look in the conceptual way. So in torsional analysis we are going to constrain the rear end with all the 3 degrees of freedom, that is translation along x, y and z axis, and we are going to apply an equal and opposite force on the opposite sides on all the 4 suspension pickup points. We can pick any amount of force to find the torsional rigidity. So for this I am going to take around 3G on one side. So I am going to apply 3G force in one direction and the 3G force in opposite direction. We can also perform a torsional analysis in front and rear end both. So for this I am going to perform for front end. In the similar way you can constrain the front end and apply the equal and opposite force at the rear end. So in this way you can perform the torsional analysis on rear end also. For the torsional analysis we follow the same process as MPCLL, in which we will create first the material, then we create property by defining cross section through hyperbeam. Then we update the component which is created earlier by importing the model itself. Then we apply forces by creating load collector for forces, and then we create constraint by and apply the constraint on my model. Then last step is to define the type of analysis by defining load step. For this type of analysis I am going to define the linear static analysis. So let's start with the hypermesh with preprocessor, and then we will use Radioss for the solver, and after that we will use hyperview for the post processing, that is result visualization. So now I will import the model in hypermesh with the line data which is in IGS format. So click on import icon to import the model in IGS format. Select the file type as IGS. You can select different types of file format also, that is CATIA, ProE, UG, SolidWorks, STEP. So the file format you have to select the appropriate file type on with the drop box. So I have a IGS format, so I'll select IGS format file. Then click on folder option to browse the file. And select the roll cage. As I have a roll cage line data, so select the file, click open. Keep all the other parameters as default and click on import. Then click on close to close the import model. So in this way you can see my line data of a roll cage structure has been imported. Now I will start with the process. First of all I will create material. So to create material for my component I will click on material collector icon. Then enter the material name as steel. Select appropriate color for material. For this particular structure I am using the material as isotropic, and enter the card image as mat 1. There are 2 cards for isotropic material, that is mat 1 and mat 4. There is a small difference between mat 1 and mat 4 card image. In mat 4 card image you can also apply thermal coefficient for the thermal analysis. But if you are not going to perform the thermal analysis, you can select mat 1 as a card image. Then click on create edit and to provide all the required material properties to define the material. So to define a material we will enter as E, nu and rho. So in this way hypermesh by default selects the material properties for steel. You can also change it by, if you have a different material you can change it by typing the material properties for E, nu and rho. Then click return to exit the card edit panel, and then again click return to exit the material collector panel. So in the model browser you can see my material has been generated. Now the next step is to define the property collector, but before property collector, defining property collector, I will first create the cross sectional for my 1D beam element. So to define the cross section of my 1D beam element, I'll go to 1D page. In 1D page I will select hyperbeam. So in 1D page click on hyperbeam. In hyperbeam panel select standard section select the standard section library as hyperbeam and standard section type as thin wall tube. Then click create. Once you click create, it will divert you towards the hyperbeam GUI. Here you will find the cross section of the hollow circular pipe. Then to define the hollow circular pipe cross section, I will first enter the outer radius as 12.7. For this model I am going to use the dimensions as 12.7 for the outer radius and 11.2 for the inner radius. As per your model and as per the cross sectional pipe, as the hollow section pipe which you are using, you can edit the inner and outer radius. So once you enter the inner and outer radius, you will find the software has calculated its area, moments of inertia, principal, torsional, constant, radius of gyration, every details related to the cross section the software has calculated automatically. Then I will go to hypermesh GUI and apply the properties on my model. So to go back to hypermesh GUI, I will click on this model view icon. So this will go back me to the hypermesh GUI. So now on my model browser you can see my beam section has been created. Now I will click return to exit the beam section panel. So now the next step is to create property collector, that is the property for 1D beam. So I will click on property collector icon to define the property for my beam elements, 1D beam element. So I will click on property collector icon. I will enter the property name as roll cage, select an appropriate color, define the type of property as 1D. Because I am using 1D elements, I will select the type for which I am going to create property as 1D. Select the appropriate card image for it. So I am going to create 1D beam elements. So I will use P beam, that is property of beam elements. Then I select the material which I have created earlier using material collector icon, and then the beam section which I have created using the hyperbeam panel. Then I just click on create edit to check whether it has picked all the required values for the beam section or not. So you can see it has picked all the required values to simulate a beam element, that is area and other planar options. So then I click on return to exit the card edit panel for P beam, and then again click on return to exit the property collector. So now on my model browser you can see my property has been created. Now the next step is to update the component with proper property and material. So to update the component, I will click on component collector. Then select the radio button as update and then click on comps. Select the component which I want to update. So I will click on select. With a no property toggle, I will toggle it down to property 1. Then click on property and select the property with which I want to update this component. Then I click on update. So my component has been updated. So why I am updating the component? Because the meshing, the 1D elements will go to this component, and to apply this 1D meshing, that is the property of 1D element and material to these 1D element, I need to assign property and material to component. So I have assigned a material property on this component. Then my next step is to create 1D elements. So to create 1D elements in hypermesh, we have one more option, that is if you go to one, that is line mesh. For line mesh panel, click on 1D page, and 1D page you will find line mesh panel. So click on line mesh, then click on lines and say displayed. So all the lines which are displayed has been selected. Then make sure the segment is whole line toggle is on instead of break angle. Then select the element size. For this I will enter the element size as 50 for this model. Select the element configuration as bar 2 and property as roll cage, which I have created earlier, and keep all the other parameters as it is and click on mesh. Once you click on mesh, it will create the 1D beam element mesh for all the line segments. Then click return to accept this meshing. So now as you can see, my elements has got created. Now the next step is to, I will first hide my geometric lines. So I will click on this icon to hide this geometry lines, and also I will change the color. So now you can see my 1D elements has got created. In Hypermesh you have one more option to see these 1D element as 3D representation. So to view these elements, 1D elements as a 3D representation, click on this transition option, that is 3D representation icon. Click on this 3D element representation. So if you click this, you will find the 3D representation of 1D elements. So if I go to mask and mask any one of the element and check whether the cross section is properly assigned to it or not. So you can see here my cross section is assigned properly on this element, and you can also select also check whether the property is assigned to this element or not. So if you select from the drop box the property by property, so the color of the property should be visible on this element. Then if you select by material, then the material color should be visible on this element or the entire elements. So you can see, so by color itself you can see whether this material property is assigned to the elements or not. Then click return to exit the mask panel. Now my next step is to create load collectors for forces and constraint. So now I will first create the load collector for force. So I will click on load collector panel. I will click on load collector icon. Enter the load collector name as force. Instead of card image, I will select no card image because I am going to apply the forces by using force panel. So I will just create the force, assign it with the proper color and say create. So on my model browser you can see my load collector has got created. So I will click return to exit the load collector panel. Then to apply load on my model, I will go to analysis. On analysis, I will click on force panel. To assign forces or to apply forces on my model, I will go to analysis, force panel. As I have already told you, we are going to apply a force of 3G in equal and opposite direction on the two suspension pickup point, two sides of suspension, all the suspension pickup points, or say 3G. So I will again convert it into line model. So the amount of force for all these 4 points in positive y direction will be, I will show you that, if I will consider a 3G force, and now if we assume the weight of the vehicle to be 400 kg, so 1G will be 4000 Newton. For 3G the total force will be 12,000 Newton. Now I am going to apply this 12,000 Newton force on 4 nodes. So for each node I am going to apply a force of 3000 Newton. So I will select the magnitude as 3000 and select the direction on which I am going to apply the force. So for torsional analysis I am going to apply force in y direction, positive at one end, and say create. Similarly I am going to apply force of same magnitude in same direction, but the direction will be negative, in the same axis but the direction will be negative. So I will, in magnitude itself I will change it and enter minus here and say create. So in this way you can see my force of equal and opposite direction has been applied for the torsional analysis. Now my next, I will click return to exit the force panel. Now my next step is to define constraint. So to apply constraint on my model, first I will create a load collector for constraint. So I will enter to load collector panel, enter the load collector name as constraint, or in industries people use SPC. So I will select SPC. Then select an appropriate color, say blue, and click on create. So on the model browser you will see force SPC as a load collector has got created. Then I will click on return to exit the load collector panel. Now I will apply constraint on my model for the rear end. So to apply constraint on my model I will go to analysis, constraint. I'm going to apply constraint or fix all the rear ends of my model for 3 translational degrees of freedom, that is translation along X, Y and Z. I am going to restrict for all the suspension pickup points at the rear end. So for this structure, the suspension pickup points are these. It may vary from structure to structure. So these are the suspension pickup points, and click on create. So now you can see my constraint has been defined. Now I'll click return to exit the constraint panel. Now the next step is to define the load step, in which I am going to define the type of analysis I am going to perform. So now the next step is to define the load step, in which I am going to define the type of analysis I am going to perform. So to define load step, I will click on analysis, load step. Enter the name of the load step as torsional. Torsional analysis. Select the type as linear static. Check the box in front of SPC and load. Select SPC as SPC and load as force. Then click on create. So in this way you can see my load step, the torsion analysis has been created. Now my MPCLR process has got completed, that is my material is created, property is created, I have assigned it to component, I have created load collector and load step. So MPCLL, my process is completed. Now I will save this file and run this file for the simulation. So to save this file, I will click on files, save as, create a new folder, say torsional analysis, save this file, enter the name of the file as torsional analysis. To run this model on using Radioss, so I will go to analysis, Radioss panel, select the export option to all, so that after during the solver process it will export all the files on that folder. Run option to analysis and memory option to default memory. Save the FEM file. FEM file contains all the element data, material, nodes, load collectors and the load step. Then click on Radioss to start the solver. So my solver window has appeared. Now as you can see, my analysis has got completed. Now I'll click on results to view the results in Hyperview. Once you click on results, it will launch a new window for Hyperview. So this is my model in Hyperview. Now first of all, I'll click on contour to see the value of displacement and stress. So I'll click on contour, select the result type as displacement and say apply. Then to see the maximum displacement, I will click on measures icon, select the static min max result and click on minimum to deselect the minimum. So only the maximum result is visualized on my model. So you can see here. So the maximum displacement due to the application of 3G load in a equal and opposite direction, the maximum displacement is coming as 21 mm. Still it's below 1 inch. So it's still my model is safe for applying a torsional analysis or torsional force of this much high. So now my next I will view the stresses. So again I will click on contour, select the result type as elemental stresses and select C bar C beam axial stresses and click averaging method to simple and apply. So my maximum stresses is coming as 61 Newton per mm square, which is if we consider the factor of safety, so around 4.5 the factor of safety is I am achieving for the torsional analysis. Now I can also view the animation. So click on the play icon, select the animation mode as linear statics, click on the play icon to view the animation. So you can, if you put it in the XY plane, so you can view the animation that I have applied the force in upward direction in this side and a downward direction in this side. So the model is moving in the same direction. So in this way we have ended with the video in which I have covered how to perform torsional analysis in HyperWorks, in which I have used HyperMesh for meshing, generating solver deck for the Radioss solver. Then I have solved this model using Radioss solver, and then I used HyperView to view the results of displacement and stresses. So in this way we have ended with this torsional analysis.